Alright guys, let's look on page 61. We're going to continue with some by parts examples today. Integration. Can we maybe reference somewhere, if you need to write it down, what our by parts formula looks like? We have a bunch of different variables going on. All right, by parts. We start with kind of a beginning integral, the one that we are trying to work backwards from. Can we label in the formula what pieces are shown in that original integral? We got up there, over here. What are we trying to identify in that original one? We got to label a dv, and whatever we don't label as dv is therefore u. All right, so we have u dv. Okay, so that's the original integral we're starting with, and after we can find those different parts or pieces, we have to fill them in to the other side, which looks like what? Yeah.
uv minus the integral of
v du. Okay, so on the other side of that formula we have u times v minus, and then the other integral we have is just kind of the reverse of the original one. Notice how instead of u dv we have v du. The variables switch. Okay, so let's go ahead and we'll reference that as we go through some more today. So take a look at your beginning integral. Again, think about detail, our little anagram. Did we even look that up? Anagram, acronym? Acronym? Okay. So can we figure out what dv should be? X. Okay, that's technically considered algebraic, which means the u variable would be arctangent. We need to work backwards from dv to figure out v, and we have to find the derivative of u to label du. Can we work backwards from x? Antiderivative? Yeah, Caitlin? 1/2 x squared, all right. And then what's the derivative of arctangent? We saw this one yesterday. Derivative of arctangent. 1 over x squared plus 1. All right, so let's go ahead and label what this original integral would look like if we set it up by parts. We need u times v, so arctangent times the 1/2 x squared. If you're multiplying things together, order doesn't matter, so you can put whatever order you want. And then we have to subtract the integral of v times du. All right, now we have to figure out what du is. Looks like we just multiply over the dx. All right, let's go ahead and clean up that integral since we're going to have to work backwards from that. Maybe we can pull out that 1/2, kind of factor it out of that integral. It's a multiplier coefficient. And then the other x squared we have would move to the numerator. So technically this new integral that we have to work backwards from should be a little bit easier to find the antiderivative from than the one we started with. Okay, so take a look at this integral. Think about your techniques. Can we try a reverse power rule? Can we try u substitution? Do we have to go through by parts again? Maybe we have to rewrite it somehow. I have no idea. What do you guys want to... I mean, I do have an idea, but I want to know what you guys... Okay, so let's think about by parts. The format for by parts is undoing multiplication. Okay, when you're multiplying two things together. Not quite here. Okay, so by parts again, we can rule that one out. We could probably rule out reverse power rule. I mean, I know we have individual polynomials in there, but again, they're being divided, so that isn't really going to work. If you thought about u substitution, what would you let u be? Yeah?
I was going to say use the separate fraction.
Oh, the partial fractions. We talked about that one, right? Partial fractions, though, and we're going to look more into that. Partial fractions, though, involved factoring the denominator. Can you do that here? If it was a -1, you could. Okay, but that +1's kind of screwing it over for us. If you thought about u sub, what would you let u be? The denominator. Okay, don't write this down. I just want you to look at something. Okay, the denominator would be u. Then the derivative would be 2x, right? But if the denominator is u, notice how we would have an x squared left up top, but we only have a single x left in the derivative. Not all of those x's would not cancel. So that's a little tricky. Maybe u substitution isn't going to work. Okay? What if we actually tried to rewrite this doing the division? Remember we went through long division when we did the partial fractions? Okay, you had to like kind of separate it. Let's go ahead and try that here. Okay, so we would have x squared divided by x squared plus 0x plus 1. Maybe we can fill in some of those 0 terms for the other one. So what do you have to multiply x squared by to get x squared? 1. So we're left with x squared plus 0x plus 1, subtract, gone, gone. Remainder is -1. So we should now be able to rewrite this integral. How might we rewrite it based off of this division? This fraction is the same as what statement? Yeah. -1 over x squared plus 1. And the quotient was 1. So you can say 1 minus 1 over x squared plus 1. Right, let's work backwards. Backwards from 1, we'd have x. Backwards from 1 over x squared plus 1.
Natural log x squared plus 1.
Not quite. Is this written somewhere else on our paper? Yeah. What could you take the derivative of that would give you this? We'd have arctangent. And then the plus c on the end. So you could leave it like that. If you wanted to distribute in the 1/2, you could. Okay, but there's our antiderivative using by parts. I'm telling you right now, what we do today, they're going to be good ones, like this one. Little thinkers. We ready? Put our thinking caps on. Take a look at 7. All right, dv and u. If you don't like the thetas in there, you can think about them as x's. What do you want to let dv be? Think about detail. Yeah. Theta, good. Which means secant inverse would be our u. Let's work backwards from dv to figure out v, and we'll find the derivative of secant inverse. Let's see, backwards from theta, we would have 1/2 theta squared. So let's think about this one. We did inverse trig functions last year. Okay, arctangent was the 1/x² plus 1. I'd probably bet my bottom dollar we don't remember arcsecant, or maybe pieces of it. You have a huge arrow pointing right at your back right now.
Well, I just have a question.
Yeah.
They write it like that all the time. Isn't it the same as like writing arcsecant?
Yeah.
So, like, how do we tell which one's which if it's just secant to the negative?
They're exactly the same.
Yeah, but what if it's like secant to the negative first power, it's like 1/secant? Like, who's the negative first power? Then they write it like that.
Mm-hmm. Yep.
Is it...
You want to give it a shot? Uh-huh.
I know that doesn't have a tangent in it.
No.
Or a sine or cosine.
No.
Let me guess it's 1/square root of x minus 1.
Close. X squared, or in this case, theta squared minus 1. And there's something else right there.
1 plus?
1
plus?
Mm-mm. Mm-mm.
Oh, that's the value of theta.
Mm-hmm. Oh, we did too. All right, let's go ahead. Now that we have our pieces, we'll go ahead and use our by parts. We need u times v, whatever order you want to write it in, minus the integral of v du. Okay, multiplying over the d theta would give you the du. So I guess technically this new integral we have should be easier for us to work backwards from. Can we? Should be easier. Can we clean it up? Do you notice anything that might happen? Let's see, maybe we can pull the 1/2 out again. Coefficient out front. The theta squared would move to the numerator. We might, yeah.
Wouldn't it cancel out with the absolute value of theta because it can be negative positive squared?
Exactly. So if you move the theta squared up top, you have 2 thetas up top, and you know you have a positive theta down below because of the absolute value. So one of those pairs would cancel out. We're left with a theta over the square root of theta squared minus 1. So let's think of our techniques. We can't do reverse power rule because we're dividing some things together. It's not going to be another by parts because we're not multiplying things. Yeah.
Is it arc sine?
Close. Arc sine would be 1 over... Actually, I think arc sine is...
No, arc cosine is negative.
Isn't it 1 minus theta squared or x squared? Yeah, it's switched. Yeah, not quite. Very close, but not quite. Reverse power rule's gone. Another by parts is gone because we're not multiplying. We can't do partial fractions because we can't factor the denominator. Yeah. Let's try u sub. What do you want to let u be?
Theta squared minus 1.
Yeah, the inside stuff. Yep, theta squared minus 1. So the derivative would be 2 theta. Alright, so let's rewrite it. We would have theta over the square root of u, and then d theta would be 1 over 2 theta du when you use your derivative equation. Will the x's, aka thetas, cancel out like we need to in u sub? Yep. Alright, so we can rewrite this as 1 over 2 u to the 1/2 power instead of a square root. Do you want to rewrite that a different way, perhaps, to help us integrate? Yeah. U to the negative 1/2. Okay, so this would be 1/2 u to the negative 1/2. So we have to add 1 to the power, which would be a positive 1/2, and then divide the coefficient 1/2 divided by that new power. One half divided by 1/2? 1, right? So we still have the 1/2 out from the front, but this 1/2 is changing to a 1 after you do that reverse power rule. Right? And we identified the u variable to be theta squared minus 1. And let's bring down the u times v part from the beginning. Bless you. There's our antiderivative. Alright. Let's check out the next one. Alright, so we're multiplying two different functions together. We can either find the derivative of at least one of them. We can also integrate at least one of them. So we could probably try by parts. What do you want to label as dv? What do you want to label as u? Think detail. Yeah. Say it again. Okay, so that's algebraic. Sine, though, is trig. Okay, so detail, t comes before the a. So this would be sine of x, and then u would be x squared. Alright, so backwards from sine, and then derivative of x squared. We can do those. Alright, so let's put it together. We need u times v. Order doesn't matter, so you can write it however you want. minus the integral of v du. All right, so the first thing I immediately see is this kind of double negative showing up in here. We could also pull out that 2 if you wanted to, because that's a coefficient. So technically, this new integral should be easier for us to work backwards from. So we either got to do reverse power. We have u substitution. We could try by parts again. Partial fractions. Probably not the case here because it's not even a fraction. What do you want to try? Yeah. We got by parts again. Notice how you're multiplying 2 different functions together. Okay, so let's go through by parts. What do you want to let dv be? What do you want to let u be? Go ahead, Caitlin.
X dv and cosine x dv.
Other way around, yep. Trig, and then the algebraic, okay? So let's work backwards to figure out v, and derivative to figure out du. We'd have sine of x and then 1. All right, so we're double dipping here in the by parts. So we have the original u times v plus the 2, but we are going to rewrite this integral using another by parts formula. So, what was that? It is, I promise, yep. Okay, so instead of that integral, we're going to replace it with the u times v minus the other integral. So we're going to have to use a bracket. We have that 2 out front. We're eventually going to have to distribute it in. If we do u times v, that'd be x times sine of x with our new parts over here. And we need to subtract the integral of v du, which would just be dx, since our derivative was 1. So apparently, this new integral should be easier for us to work backwards from. Can you work backwards from just sine? That'd be negative cosine, right? So our subtraction would change to a plus, and then plus c on the end. You can distribute the 2 in if you wanted to. You could leave it like that. Either way is fine. Okay, so we might have to double dip, maybe even triple dip sometimes. Okay, Maddie's face. Foreshadowing. Let me see. Yep, we're foreshadowing. Yep, we're foreshadowing. Okay, so it's all about thinking about how you can take that next integral further. Okay, what about the techniques that we've been talking about? So, without further ado, let's try number 10. Okay, multiplying 2 different functions together, you can easily take the derivative of at least one of them. You could easily take the antiderivative of at least one of them. So by parts should be a good way to go. What do you want to let dv be? What do you want to let u be? Think detail. Yeah. There we go. So then t to the 4th, we got du, or sorry, u. Work backwards from dv to figure out v, derivative of u to figure out du. All right, so by parts. U times V. Order doesn't matter. And then we gotta subtract the integral of V du. If we were to multiply the 1/2 e to the 2t times the 4t cubed, 1/2 times 4 would be 2. We'd have e to the 2t and then a t cubed dt. So technically this new integral should be easier for us to work backwards from. Can we do reverse power? Can we do u sub? Can we do by parts again? Partial fractions? We gotta do it again. All right, so dv, and what's u? Just this piece?
So t cubed.
Oh, t cubed would be what?
U.
That would be u. Okay. And maybe we'll let the 2e to the 2t be the dv. Okay. I know in the other examples we've pulled out the 2 as a coefficient. Okay. You could do that. Let's say you didn't want to. Maybe we'll see what that looks like in this case. So backwards from dv, and then derivative of u. All right, so if we fill in what we have 1/2 t to the 4th e to the 2t, the original u and v, minus this new integral that we are using by parts for. So we're going to have to use a bracket to group everything based off of our formula. We would need u times v minus the integral of v du. Maybe at this stage in the game, do you guys want to distribute in that minus sign to get rid of those brackets? One less symbol in our expression that we have. So apparently, this new integral should be easier for us to work backwards from. Reverse power rule, reverse power rule, u substitution, by parts again, partial fractions. What was that? Haunt you? Tis the Halloween season, right? Okay. So we're triple dipping. This is the third time we've had to do it. dv, we have the exponential. U, we have the algebraic. See, this would be 3/2 e to the 2t. All right, I'm going to start moving over here. So we have 1/2 t to the 4th e to the 2t minus t cubed e to the 2t. That's just the original stuff we had over here. Plus And now we're going to rewrite this integral using by parts. We don't really have to worry about brackets anymore. We did before because it was subtraction that we'd have to distribute in. But since we're adding, those brackets aren't necessary. We need u times v minus the integral of v du. 3/2 times 2 will be left with 3. So apparently, this new integral should be easier for us to figure out. What do you guys want to try? Let's do by parts again. Do you guys realize though how we're kind of chipping away at it? Do you notice how we started with a t to the 4th, right? And eventually we got down to a t to the 3rd. And then we got down to a t squared. And now we're down to a t. Okay? Literally, we're down to a t. Okay? So let's try it again. dv will have the exponential. U will have the algebraic. Backwards from dv, derivative of u. All right, 1/2 t to the 4th e to the 2t minus t cubed e to the 2t plus 3/2 t squared e to the 2t minus bracket, because we're going to have to distribute that negative. So in this new by parts, we have u times v minus the integral of v du. And notice how du is just dt. Note to self, give you more room, right? Alright, so we have 1/2 t to the 4th e to the 2t minus t cubed e to the 2t plus 3/2 t squared e to the 2t. Distribute the negative, or subtraction, minus 3/2 t e to the 2t. Distribute the negative, plus whatever this new integral would give us. Can we work backwards from just that exponential? Finally, right? We would have 3/4 e to the 2t plus c. We doing okay? We hung in there? No, happy? By a thread, maybe. It's a process. By a thread. You gotta be organized. Yep, you gotta be organized. Alright, we'll check out this last one before the bell rings and then we'll call it a day. Okay? Solve that derivative equation if z is 5 when x is 1. Okay, so if it says solve a differential, a derivative equation, we got to separate those variables, work backwards. So in this case, if we separate, that's real easy because we just got to move over the dx. But now we got to integrate both sides. You got it, Autumn. Backwards from z, or sorry, dz, would give us z. And how might you want to work backwards from the right-hand side?
1/4 x to the 4th. Oh, wait, there's a minus.
You're multiplying two different functions together. You can find the derivative of at least one of them. You can differentiate at least one of them. Or sorry, take the antiderivative of at least one of them. Let's try by parts. What do you want to let dv be? We got that algebraic of x cubed, which means u is the natural log. Backwards from v or dv, 1/4 x to the 4th. Derivative of u, derivative of natural log, 1/x. Good. All right, so by parts on the right-hand side, we need u times v minus the integral of v plus u du. So this new integral should be easier for us to work backwards from. Can we clean it up? Notice how we can cancel out an x, so it'd be left with x to the 3rd. Looks like we have a reverse power right there. So add 1 to the power, we would have an x to the 4th. Divide the coefficient by that new power. 1/4 divided by 4. Ooh, close. 1/16. You gotta multiply them. We don't know the bounds, so we need that plus c. But we're gonna figure out what c is, because didn't they give us a particular value for z and x? All right, so 5 goes in for z. We'll plug in 1 for all the x's. Natural log of 1,
0.
that's 0. So we have to add over a 16th. 5, we'll write it as a mixed number. Okay, 5 and 1/16. For those of us that are improper fraction people, this would be 81/16. Okay. So let's see, our original function for z would be 1/4 x to the 4th, natural log of x, minus 1/16 x to the 4th, plus 5 and 1/16, plus 81/16, whatever you want to write. All right. We're used to that. We've done separating variables, working backwards, using a particular point to find a solution. We've done that, okay? But what we're adding to our repertoire is this new process for integration, this new technique. Okay, so it's in our little Batman belt, if you will. Our little, what does he call that? His utility belt. Okay, it's another tool we have at our disposal. All right, we'll stop there. We're going to look at some good ones. Tomorrow's Free Response Friday, so we'll look at some good ones next week. But you guys aren't going to be here Tuesday, so we'll pick up on Wednesday.
That's amazing. You know, I really wish I was born a year